Okay, so we're now at a stage where we've got the second graph drawn with 2 lines of best fit, and we've worked out the gradient of each of those lines, and then come up with our final gradient value with its associated uncertainty. And now the last little bit we need from the graph is the y-intercept. So we're going to trace these lines back to see where they hit the y-intercept, and then add that information so that we can use it on our final equation. Now, the lines of best fit, we'll put a ruler across them and see where that tracks back to. And in both cases, it's going to be below the bottom of the graph. So for this, I'm going to need another piece of paper, or I have the ability to do this on a larger bit of graph paper, but it works really well if we put the graph above another piece of paper. I could staple it, stick it down if I wanted to, but I'm quite happy that if I just mark on where the corner is, so I can keep track of it, make sure it doesn't slip too much. So I'm going to extend that black line back to where it intercepts this axis. So I'm just going to extend the axis down a bit so we can see that. And I'm going to put the ruler over the black line first, and then probably should have used the black pen for that. And then do the same for the blue. Okay. And I've checked that the little corner that I drew on there, just to make sure the paper didn't slip, is still in the same position. So I'm pretty happy with that. Now we can measure the scale of the graph, and I can see that one of the big boxes on the graph paper is about, I think that's 1.2 millimeters. So I can draw in some of those down here. So at 1.2 we would be at -5, and then another 1.2 down from that. It's going to take us down to here. And then I'll measure another, oops, just line that up again. And that's all we need really. So we've got -5 there, and -10 is that mark there. So in order to get the values of these reasonably accurately, I might need to know how big each of the small boxes are, and they're just over about 2.5 mil. And so if I come down here, I'd say I've got 2.5 to there, and another 2.5 would take me to there, and then 2.5 is about there, 3, that's going to be about there. So I've now marked on -6, -7, -8, and -9. And so I'm going to say that this blue line is between about -8 and about -9. So the blue line has a y-intercept value. It cuts across this intercept, it cuts across this axis at -8.5 seconds. And the black line cuts across at negative, I'd say it's probably about 6.5. So the black one is about -6.5. Okay. From that, I'm going to write down here that the y-intercept excuse my writing. The actual value we state for the y-intercept is going to be the average of these two, and so that's going to come out as negative 15. So it's negative 6.5 plus negative 8.5, and then to get the average we're going to divide that by 2. So that's the same as negative 15 divided by 2, which equals negative 7.5. And we want some uncertainty in that as well. And the uncertainty, like we did for the gradient, it's going to be plus or minus half of the range. The range of the y-intercept, so the y-intercept range is going to be negative 6.5 minus negative 8.5, and then divided by 2. So minus 6.5 minus 8.5 is going to come out at plus 2, and dividing that by 2 gives us plus or minus 1. So the y-intercept uncertainty, I'll just write down that the range is comes out as being 1, and the y-intercept uncertainty is therefore plus or minus 1. Now, because our value here is two significant figures, and these values are two significant figures, that should actually be 1.0. And so our y-intercept is, so final y-intercept value is negative 7.5 plus or minus 1.0. Okay. Now we're going to put these two pieces of information together, the gradient and the y-intercept, to write our mathematical relationship for how the time varies with the change in height of a column of water. And for this we use the equation of a straight line, which is y equals mx plus c. We don't refer to y or x after this, and so our y quantity is time. So I'm going to use a big T for time, or, well, I'll write it out maybe, no, we'll use a T for time, equals m is the gradient, and so that's where we take our 12.4 plus or minus 0.4, and then we're looking at x, so whatever our x value is, our x variable, and that's the square root of change in height. So we write in here square root of the change in height, and then c is the y-intercept value, and so that is minus 7.5 plus or minus 1.0. And so we write up here minus, so it's plus c, but because our y-intercept is negative, it becomes a minus sign. 7.5 plus or minus 1.0. That is our final relationship for how time varies with square root of change in height. It's probably worth saying that at that stage we would be at an achieved at least for the experiment. Oh, sorry. No, we need to compare that with a theoretical equation in the actual assessment. So you'll be given an equation which will look something like that, and you'll need to write them side by side and say how similar they are. Like, does the theoretical gradient fit within 12.4 plus or minus 0.4? And it doesn't matter whether it does or not. The important thing is that you've compared them.